Hello, this is Elder Tehila from the Coven of the Open Mind, and you're watching Metaphysics 101. Hail and welcome. The topic this time is on quantum physics. This is the first of two lectures on quantum mechanics. This one will be about what is specifically termed quantum weirdness, which refers to the bizarre manner of physics on the level of particles and in what we refer to as the quantum realm. In the last two lectures, we spoke about the physical and astral realm as we compared our daily existence with the nature of massive bodies in space. And what we saw is that these different realms are really the same space, they're the same universe, but the physics functions very differently because large, massive objects experience certain aspects of the same equations that would have been negligible when you calculated out how things worked for our physical plane of existence. So we have these different kind of realms, and it's all physical space. It's really all the lowest plane of existence. It's all our physical universe, but the realms really refer to scales, if you will, upon which physics is different because, you know, the nature of the objects in each frame is very different. It's sort of like relativity, or just thinking about it like how it's the same physics, but that there's different frames of reference. And so the astral realm is the reference of celestial bodies, big, massive objects in space, things that are massive enough to influence the nature of space-time itself, as we spoke about. The universe is background independent on that in that realm, so all of the equations don't depend on a fixed background. Then you have the physical world, and that's the world we live in, the world that we all conceptually understand, which we haven't spoken too much about. We're not going to touch much on classical mechanics because it's just not particularly relevant to the subject of metaphysics. I mean, calculating how long it'll take a roller coaster to go from the peak to its lowest point and etc. is not particularly helpful when it comes to understanding the higher planes of existence, because it's really solely focused on understanding how the physics of our plane of existence works in our physical realm. So we're not going to touch on classical mechanics. We're not going to touch on the physics of our realm too much. Most people have a conceptual understanding already. You know how gravity works. You know how to throw a ball. You don't have to study physics to learn how to be good at sports. Lots of people who are good at sports know nothing about physics, right? Because you can just have an intuitive sense for it, and that really is what physical intelligence is that intuitive sense of where you are in space in relation to everything else in space. You know, you have physical, go to the larger end of the spectrum, you get to astral. Then you have, going the opposite way to the lower end of the spectrum, you have the quantum realm. This is often in Wicca referred to as the elemental realm because they named it before we knew what quanta were. Quanta comes from Latin. It means the smallest part, the smallest, you could break something down. So quantum sounds like this big scary word, but all it means is that we're talking about particles. We're talking about the fundamental building blocks of matter, particles, forces that interact on the level of particles. So we're not talking about gravity, because gravity is largely a force between macroscopic objects, which are large systems of particles, and as a result of the particles all kind of interacting with each other in the system that they're in, that results in them acting differently. They act macroscopically. They obey different physical laws. Okay, that's what differentiates whether we're talking about the physical realm or the quantum realm. Okay, if we're talking about the quantum realm, we're talking about individual particles, not systems of particles. Particles are just energy. We spoke about this in the past, and I hope you are all developing a sense by now for this fundamental fact that energy equals matter times some constants, right? Energy and matter are one and the same. So if it exists, it has mass. If it has mass, it has energy. And of course, for certain particles like light, because they are massless, therefore their energy is equal to how they move. Everything that physically exists is both matter and energy at the same time, which means that particles are like physical things. You could think of them like balls, and they are waves, which you can think of like how you might envision a wave in a pond. If you drop a rock into a still pond, you get ripples, lots of ripples that come out in a circle from where you dropped it. Points where there is more water and less water. Sound is another kind of wave that many are familiar with in the physical world. Sound is air waves. Okay, so you hit something and that produces more air, which forms like a little packet of air that flies out from wherever you hit. And that little packet of air is like a wave. If you want to see sound waves in motion, just look at a speaker. So macroscopic waves, like sound waves and ripples in a pond and waves at the beach, in the ocean, function very similarly to particle waves. However, particles are waves of energy itself. And where the peak is, you have a surplus of energy. And where the trough is, you have an absence of energy. And so you're more likely to find a particle if you go to the particle and say, where are you located in space? And you ask the particle that question. And you do that by sending another particle at it. And then it responds by sending a particle back to you with its answer. Okay? That's how you communicate. You can go reach out to an electron and say, hello, electron, where are you? By sending in a photon. Then the electron receives the photon and sends a photon back, and that's how you know where it is. If you do that, then you will find the electron in one of those troughs. You will find the electron in one of those areas where there was a lot of energy. Those are the likely spots to find an electron for all intents and purposes. And so you can think about the probability curve of the electron, of a particle, as being essentially an equation that is the particle is located a little bit here, a little bit here, a little bit here, a little bit here, and each of those locations is multiplied by a constant. And that constant represents the probability of finding the particle in each of those locations. So the particle is a sum of all of the places a particle could be and all of the directions and speeds the particle could possess. It is a sum of where the particle is over all of space-time. Because think, it is a wave. Okay, waves don't... If I would ask you, if I dropped a pebble in a pond and I would ask you where in the pond are the ripples, you're going to say everywhere. They're all coming out of this one location and going out like a circle. That's exactly what a particle is like. If a physical macroscopic being goes to a particle and says, where are you located in space? The particle will collapse into a single location and say, I'm here. If the macroscopic physical being looks away, then that particle will resume its state of superposition and exist in many locations at once as a wave. Okay? It doesn't really make any kind of rational sense, and that's why it's very hard to conceptualize this scientific principle, which is called superposition. Particles are not half here and half there. You're never going to find a half of a particle. So because particles are a wave and a finite object, an infinite wave and a finite object at the same time, because of what is called wave-particle duality, and because particles exist in a superposition of all of the states that they could be in, they are essentially waves of existence itself. And because of that, they experience a very different physical reality than macroscopic objects, than humans, you know. So our day-to-day existence and the physics that we understand conceptually, that we just intuitively understand, does not exist for particles. They behave in ways that make absolutely no sense to us, but which are completely normal for them. One of the key principles that affects the way particles behave is the uncertainty principle. Now, the uncertainty principle is not unique to particles. It is true for all waves. You know where a wave is located and what it looks like, or you know where it's going. So because particles are waves, that's true for them as well. There is a level of uncertainty. A particle has different rules. You can only see the effects on very small scales for particles specifically, not systems of particles, individual particles. The reason for that is because particles interfere with each other. There's something called the double slit experiment that does a really great job of demonstrating what I'm talking about. Basically, with the double slit experiment, you have a light beam being fired at two slits, and then on the far side, there is a screen. And when you shoot the particle through the two slits, you don't see the particle going through one slit or the other and showing up as a beam, as like a localized beam in the other side. What you see is actually an interference pattern. And that's because the wave from the particle goes through both slits and then interferes with itself. That's how you can see it clearly demonstrated, and they interfere with each other. Now, if you were to take a picture of the particle as it went through one slit or the other, that requires you to shoot a photon at it and receive a photon from it. So that requires an interaction with the particle. And if you interact with the particle, that will force it to collapse into one screen or the other. And so taking a picture of the particle while it goes through the screens will cause the particle to collapse into one or the other, and you will actually see all the particles appearing in through one slit or the other, as opposed to seeing the interference pattern. What this does show is that a particle can interfere with itself because it goes through both slits. If the particle was only in one place in space, then it would have to go through one or the other slit. But you know it's in both places at the same time because it will always go through both slits unless you interact with it and cause it to collapse into one state or the other. If a physical macroscopic organism is interacting with the particle, it will behave macroscopically and act like a single object. However, if it's left to its own devices, it will always act like a wave, interfere with itself, interfere with other particles like it, and if enough particles come together and interfere with each other, you wind up with complete decoherence. That means none of the particles are in superposition state. When you can think about it like when you throw a bunch of pebbles into a pond, you no longer have the nice ripple pattern, you just have chaos. So, particles can be forced to collapse and act like physical macroscopic objects by being observed by macroscopic objects or by forming macroscopic objects. If you get large systems of particles together, they form atoms, and atoms come together to form elements, and elements come together to form physical objects like rocks, trees, humans, anything you can think of. And those are very large systems of many, many particles. All of those particles would exist as waves, but they can't, because when they start trying to be waves, they interfere with each other and collapse into nothing, into chaos. So there is no capability of a system of particles to sustain a superposition state, with it, which is actually a major challenge when it comes to quantum computing, because the number of particles you can put into a system before they collapse out of their superposition states is not very high. You have to keep the particles separated somehow because there's special rules. The particles have properties that require them to keep track of who they are. So, you have this model of an electron where you have a core and then you have these electrons shooting around the outside of it. And it looks like balls. in this big complicated system where you have one big ball in the middle and a bunch of little balls orbiting around the outside. But in reality, the balls orbiting around the outside are really just a cloud, essentially, because nobody really knows which particle is which. One has one kind of spin and the other has the other kind of spin. And the fact that electrons are half spin particles is what forces them to have two in each energy level. So you have two close to the atom, and then two a little further out, and then two in that same level a little further out, and then two in this next level further out, and they all just kind of fall in like they were getting on a bus and filling in the bus seats. There's like a specific way in which the electrons fill in those bus seats. That is actually how you can derive the periodic table of elements. So when it comes to particles in systems, even particles that are bound into atoms are oftentimes no longer in superposition states, but sometimes there is some level of uncertainty going on because atoms decay, and there's uncertainty with relation to energy and time as well as energy and movement. All of the dimensions are really the same thing, so the height, width, depth, and time are really all the same thing. That principle is called decoherence. And it's basically the reason why macroscopic objects are not capable of behaving the way particles do. Now, particles, how do they behave? We've spoken so far about what makes particles different than macroscopic objects, which are made of particles. Now let's talk a little bit about what particles are capable of. Particles move through walls. How do they do this? They do this because they're probability curves, and there is a small but finite chance that they could already be on the other side of the wall. They could just fold through time and space and just suddenly be in a new place. They can basically teleport to a new location. But it's not like they're going from one place and moving to another. They were already in both places. Particles exist as probability curves. That means that particles exist all over space and time. If I were to shoot a particle out from the planet in one direction and I put targets all over the Earth, if the particle was shot in one direction, it could be found on the other side of the planet at another target. If I had two targets so close together that the particle should hit both of them practically at the same time, it still is going to hit only one of them. It will choose one. It will just pick one, and that's where it is. And it's random. And we'll talk about randomness in the next lecture, which is also on quantum mechanics. But essentially, particles, because they exist all across space and time in a superposition of all the states that they could be in at all times, therefore particles can do very funky things. They can fold through time, they can remember alternate timelines, they can go through physical objects. Now, not every particle that you shoot at the wall is going to go through to the other side. Okay, some of the particles are not going to go through because it depends on probability. In fact, only a very small number are going to go through to the other side. But you can shoot so many particles at the wall so quickly that it doesn't matter. Still, a significant number of them will go right through to the other side. This is how quantum tunneling works, where you actually can shoot high-powered particles at something in order to send them into the other side and get a picture of what the inside of something looks like without damaging the outside. A person can't run through the wall because a person does not exist in a superposition of states. If you actually did the math, you can actually see very clearly that there is a very small but finite chance that a person could magically appear on the other side. But it is such a small chance that you would have to run at the wall an impossible number of times in an impossible length of time. Like, it's literally, if you did the math, it is literally impossible. It is physically impossible. Mathematically, it's possible, but physically, it is not. You would have to run at the wall so many times in a fraction of a second in order for you to appear on the other side of the wall, and you just can't do that. You cannot move that physically quickly. But a particle, you could send particles at a wall at a rate that is very, very rapid, lots and lots of particles per second. And you know, a small percentage of them will go through, will magically appear on the other side of the wall, but that small percentage is enough for, you know, quantum tunneling to do its thing and get you an image of whatever it is that you're looking at. So if a macroscopic object asks a particle to behave like a physical object, the particle will do so. It will collapse into a finite state. It'll say, here I am, or this is where I'm going, and it will give you the answer that you ask. However, if you do not ask the particle any questions, it will exist in a superposition state of all the places that it could be going and all of the places that it could have been, and it will be everywhere that it could be located all at once, which I realize does not make a lot of rational sense, but that's why it's very difficult to have a conceptual understanding of quantum mechanics, because physical objects don't experience this aspect of time at all. Our day-to-day existence is devoid of time dilation, and for us, we are very much confined by our physical forms and by the physical laws that govern physical forms. The other thing that we learned from quantum weirdness has to do with a little bit of biology as well. So, our physical bodies are made up of systems of particles, as we said, but the nervous system is essentially an electrical system. Because our central nervous system is essentially run by energy fields, it can be influenced by the movements and the subtle changes in this energy, you know, the energy of existence itself, which is not something that you would physically sense, but something that you could sense through your metaphysical centers, through your central nervous system. So it's kind of bypassing your senses. So we're talking about things that are so subtle, you can't see them. You can't see auras. If another person has an aura, you can't see it. It's not producing light, or else you could see it with your eyes. So if you can't see it with your eyes, then it's not physically there. If it's metaphysically there, what we're saying is that, you know, the uncertainty of some of the particles in that person's system, that, you know, their electrical system, that is capable of being a little in flux, those are producing, you know, a certain wavelength of energy itself that I am picking up on using my metaphysical center, and then I am converting that into something my brain can comprehend, which is physical sight. And so in my mind's eye, I might see a color, but really I'm just feeling something. I'm just feeling it through the energy part of me, the part of me that is just energy, okay? Because everything fundamentally is just energy, even empty space. This would be the scientific basis for the idea behind chakras, behind metaphysical body centers that pick up energy and perceive energy without having to physically sense it, without having to see it with your eyes, without having to hear it. For now, all you have to take away from this is that particles exist in superposition states. Therefore, they are all over time and space at the same time. Our physical bodies are in part made up of electrical fields, which means that we are susceptible to the tiny perturbations in energy. If you have any questions, you can feel free to email us at covenantopenmind@gmail.com or drop a comment on this video. Happy to help you understand the subject. So I hope you guys found this helpful and you can take away the right things from this topic. I look forward to doing our next one and wrapping up quantum physics, and then we will move on to other more exciting branches of physics, and it gets only more exciting from here. So stay tuned, and I look forward to talking to you again soon. Blessed be.